Hi everybody, today unfortunately I didn't record the lab, so I decided to make this video for those who would attend today's laboratory. Today's topic is about ensembles of models, but before we go to ensembles, let's talk about how to build a decision tree for regression. Last time we saw an example how to build decision tree for classification using the entropy for splitting into classes. And let's look at the following problem. We have the following table of data, 1, 2, 3, 4 points, and predictions for these points. And we should build a decision tree with quality measure mean square error instead of entropy in case of classification. And with 3 leaves. So let's get started. The first split we can do for x greater than 0, greater than 1, greater than 2, greater, okay, and that's it, greater than 2. And if we want to minimize the mean square error, then here with some calculations, the derivative of this will give us this sum, and then the optimal target will be the same as the mean value. So this difference yi minus mean value corresponds to the variance. So we should choose our predictions to minimize the variance. And of course, it's obvious that we should split the first time like this, because if we have 6 and 100 in one class, the variance will be 94 squared, which is a huge number. So the first split we do with threshold x greater than 2, and we have prediction in one class 100, and in the left class the mean of these numbers 4, 5, and 6. And it's equal to 5. Now the impurity of the right leaf is 0 because we have only one element, and the mean will be the same number, 100, so y minus mean will be 0. We don't need to split this node, but we can split this node because we have here 3 axes. Let's try to split this node. We have two options: set threshold x greater than 0 or x greater than 1. Let's try first one. So in the left class, we will have only one number, 4. And in the right class, we will have the mean value of 5 and 6. If we try to calculate the impurity, let's do that for the first split. For the right class, we have only one element. It's 1 over 1 times 100, and mean is 100 as well. So it's 0. And for the left class, we had 3 elements, and mean value 5, will be 4 minus 5 squared, plus 5 minus 5 squared, plus 6 minus 5 squared, it will be 1, 0, 1, so 2 thirds. And the equality factor here, actually quality has this form, but because the first term doesn't depend on the splitting, we can just minimize these two terms, negative terms. So I'm using the Q tilde, and which we can call cost instead of quality, and minimize it. We have 3 elements in left class and 4 elements in total in the previous node, times impurity 2/3, plus we have 1 element in the right class and impurity 0, so it will be 0.5. If we would choose, for example, another splitting, as I mentioned, 6 and 100 in one leaf, then we would have impurity here. The mean value around 50, so 6 minus 50 squared plus 100 minus 50 squared, it would be a huge number. So the best split we could do, just minimizing the variance. Let's look at the second split. In this case, our right branch contains 2 numbers. 5 minus mean value squared plus 6 minus mean value. We'll get 1/2 here, 1/2 here, where 1/4 will be 1/4. And in the left class, we have only one element, and so it will be 0. And quality factor will be 1 over 3 times 0 plus 2 over 3 times 1 fourth, and it's 1/6. If we split in a different way, like this, x greater than 1, we have here 4 and 5. Mean value is 4.5. Here we have 6. And if we calculate the impurity, here will be exactly the same number, because 4 minus 4.5 is 1/2, and negative, and 5 minus 4.5 also 1/2. But if we would split in a weird way, like 6 and 4 in one class and 5 in the other, we would get here a mean value 5. And this would be the worst case, because the impurity here would be 4 minus 5, 1, and 6 minus 5, 1. It would be greater than previous splittings. And because we've had two equal values of quality or cost, we can choose arbitrary one of the splitting. And now we have exactly 3 leaves. Now let's look how scikit-learn could solve this problem. The let's run this code. So we import the decision tree regressor. We indicate the maximum number of leaves. Then we create our data, x, 0, 1, 2, and 4. We reshape it to make the one column, and the rest number of rows. In this case, it will be 4, because our model takes as input matrix, not array. Fit the regressor and use function plot3 to plot the resulting string. Here you can see the first split along x equals 3. You remember we split it along x equals 2. I believe the scikit-learn takes the mean value between 2 and 4. So splitting goes along 3, and it classified, splitted our data into 2 nodes. One is the terminal node or leaf with value of 100 and with 1 sample, and impurity or squared error 0. And the next node, it's split it along 0.5, which is the mean between 0 and 1. And we have one value 4, and here we have 5 and 6. So let's try to visualize this result. I created the array of numbers from 0 to 5 just to plot the continuous function. And let's plot our predictions and our data. Our data are red points: 4 for 0, 5 for 1, 6 for 2, and 100 for 4. And here is our decision tree, which is the function of arbitrary value x. Now, when we understood how to plot individual decision tree, we can talk about ensembles of models and ensembles of tree in particular. There are two approaches, main approaches for ensembling of models. Or compositions of models. The first one is based on the voting. For example, if you have several experts and they give their decision about something, we choose the most popular decision. And in case of regression, if our experts give us numbers, then we take the average of these numbers. The second approach is boosting, and the idea of this approach is that first we ask one expert, and if he makes mistakes on some predictions, then we ask the second expert, but we ask him to give his expertise only about that values on which the previous expert was incorrect, and so on. So we train each model on the errors of the previous models. So these are two main approaches. Let's start from majority vote. I created these random data points, and let's try to train two different decision trees. To one decision tree, we will feed 90% of our data set, randomly selected. And to the second decision tree, we also will feed 90%, but of different random selection from our data set. And let's see, there is function plot decision regions, which will show the decision boundaries of our classification. So this is the result for the first tree or expert, and now we split again our data set and train a new decision tree, and we see that their predictions are different. Now let's try to train 20 classifiers, 20 decision trees on different subsets. So here is the parameter 20 estimators, and my estimators are decision trees, and the size of subset is 90%. And here is the result. So the result is something between the previous two equations. Now let's try to do this for regression. I created two examples, sinusoid with some random points. And now we train 10 decision trees of depth 2. And here is the result. As you remember, for regression, we take the average of the predictions. So on this plot, you can see these 10 decision trees in blue, and in purple, the mean value of these trees. And you can see that our trees have pretty large variance, but the mean value is closer to our original data. And here it's time to talk about the decomposition of our error on bias and variance. So usually our models have noisy data, and we can't do nothing with this noisy data. So this is one source of the errors. The other source of errors is our model. So, for example, if I train linear regression, 10 linear regressions on the same sinusoidal plot, we will get this figure. You can see that each individual line is very close to the mean value, but at the same time, these lines are very poor predictions for our sinusoid, so we can say they have high bias. So simple models usually have high bias, but at the same time they have small variance. And decision trees instead had high variance, but smaller bias. And so our error can be split into these three terms: the bias, the variance, and noise. How can we make bias smaller to take more complicated, more involved model? How can we can do nothing with noise, you remember? How can we eliminate and or reduce variance? To reduce variance, we can aggregate several models, and in that case, we will get variance n times lower than one model, but there will be also another term, covariance, which will be smaller if our models are independent. And here the idea of Bootstrap appears. If we want to make our models more independent, we can try to make their predictions more independent. In previous case, we trained on the subset of the entire data set our models to make a little bit difference. But there is also another method which is called Bootstrap. Bootstrap is the choice with replacement. So for example, if we have numbers, objects 1, 2, 3, 4, 5, 6, and so on. Let's say we have only 6 objects. We can randomly select 6 numbers, but we can choose one number several times. So, for example, we can select first number 2, second number 5, third number again 2, then probably 1, then 6, and then 3. You can see that in this sample, we didn't select object number 4, but we choose object number 2 twice. So it means that we gave importance to the second object higher than to the others. And this approach is called Bootstrap. It's important that we use the entire data set without using validation set here. Let's try to aggregate 10 models, 10 decision trees with Bootstrap. By default, if we use Bayesian is Bootstrap aggregation for aggregating. Then by default, it's using the Bootstrap. You remember in previous case, I use this parameter Bootstrap equals false. By default, it's true. So here is the result of Bootstrap aggregation for our sinusoid. Now, let's take a look at this problem to understand better the idea of Bootstrap. A machine learning engineer has found the following data set. And also, there were two first nodes of the tree. So let's draw that. There were two nodes, one with decision x greater than 2.5, and the second was with threshold 3.5. So he decided to calculate the values in the leaves of these trees using Bootstrap. And using Bootstrap, he had for the first three these samples 1, 1, 2, 3. So if x greater than 2.5, then only 3 is greater than 2.5. And here we have 1, 1, and 2. And he is using mean squared error, so the value in this node will be just the average of 1, and 6 is the value for x equals 1, again 1, and 2. For 2, the value is also 6. So the value in this leaf will be 6. But for 3, we have only one number, 12. Let's take a look at the next possible tree. X greater 3.5, and our Bootstrap sample is 2, 3, 4, 4. So we have twice 4 in the right class and 2 and 3 and in the left class. So for twice 4, we will get average 18. And for 2 and 3, we will get 6 plus 12 over 2. 18 over 2 is 9. So these are predictions for the second tree. Now I hope you understand better the idea of Bootstrap. So we said that this Bootstrap approach helps us to make the predictions more independent. There is one more option how to make the predictions independent, to choose to use not all the features for training, but only some features for training. And if we use just a subset of features for training of individual decision tree, sometimes such trees are called extreme trees. And the ensemble or bedding of such trees is called random forest. And now let's try to train random forest for our simple examples. And in random forest, there is parameter for the number of features that we use, max features. This parameter is calculated automatically. There are some recommendations how to choose it. I will give them later, but you can also set it manually. The number of features chosen randomly for training of each tree in the forest. So I took 50 trees and depth of each tree is 5. And here is the result. You can see that it's pretty unbiased, but still some variance because there were noisy data. Probably if we will use small number of trees, it will be better. Take deeper trees. Still not so good. Well, and now let's train a random forest on our classification data. And you can see that comparing with simple majority voting without Bootstrap and without random selection of features for training of one tree. The decision boundary is more smooth compared with the previous one. And here is the recommendation for maximum number of features which we use. It's the third of features for regression and square root of number of features for classification. One more thing about random forests is out of back evaluation. Because we use the entire data set and, we don't have validation set, still we can evaluate our model using so-called out-of-bag evaluation. Now I will show you how it works. So suppose we have 1, 2, 3, probably 4 decision trees in our forest. And Bootstrap shows these values. Let's say we had numbers from 1 to 6. So let's say it shows 1, 2, 2, 3, 1, 6. The next tree was trained on the features, let's say 5, 6, 2, 1, 5, 2. Another tree was trained on the features 3, 1, 2, 5, 4, or actually 4. And the last tree was trained on features, let's say, okay, 4, because I did this before. 4, 3, 1, 1, 5, 2. Hopefully it's better not using 2. Let's say 3. Now, when we want to evaluate our forest, our ensemble on the data point 1, we will, okay, we can't evaluate in this case because we should take 3 which didn't see this value. Okay, let's say 2. To evaluate 2, we will choose only tree number 4. To evaluate 4, for example, we will use the composition, the bagging of trees 1 and 2, because the element 4 wasn't used in their training. And because we have usually more than 4 trees, like 50, 100, then we would have at least 1 tree for each element. So we can do evaluation by the trees which were not trained on this data point. And this is called out-of-bag evaluation. And you can indicate this parameter true in your training, and then you can get this value from your classifier out-of-bag score. Decision trees are very good models, or sorry, random forests are very good models because they don't use any hyperparameters. Both parameters, like the number of trees, like the depth of trees, like the number of features for selection, are recommended in this paper, and we don't should care about it. But why we need the other models, the boosting? Let's talk about some problems with random forests. One problem is that it takes time to train a lot of trees. But more important problem is that if we choose in not very good basic model, and then we do the aggregation of these models. So if one basic model has a large bias, then you remember that aggregation can reduce variance, but it can't reduce bias. Like if we take many linear regressions for sinusoid, we will never approximate it with lights. That's why another approach was proposed, boosting. Assume here we have k models, and our final model is the sum of these models. And the first model we will train just minimizing our loss function. When we train the first model, we should train the second model. And originally for boosting, we just take the sum of first and second models. First model is known, so it gives us some numbers, and we should find just parameters of the second predictor. And we can find the second, and we then can add third and try to find the third model and so on. Let's look at the example of mean squared error loss function. So if our model contains for now only two simple models, A1 and A2, let's group these summands in a different way. So let's subtract from target the prediction of the first model, and then subtract the prediction of the second model. It's easy to see that the second model tries to minimize the errors of the first model, because target minus the prediction of the first model is the error of the first model. Let's look at the example of such approach. So I created three decision tree of depth 1, which is called decision stump. And I trained the first decision stump on the sinusoid, and then subtracted the predictions from our original data. This plot on the right represents the error of the first model. Then we train the second decision stump on the error. So here is the result. Then we sum the first and second model and subtract from the target. So we get again error, but after the sum of two models. And train the third model, the third decision stump on this error. And then we sum these three models, and you can see that the sum of these three models is not that approximation of our sinusoid. If we take a little bit deeper decision trees like depth 2, the result will be much better. So here is the result of boosting of this tree. But you can see here a little bit variance. Okay, there is another problem. I won't go through it because I wrote here the solution. I just wanted to show that for decision trees, we can use not only the minimizing of variance in leaves, but we can use the different quality functions. Such, in this case, we have regularization term. We want to make a little bit smaller predictions in one leaf. Again, it's all made to increase the independence of individual tree. And such models are called extreme trees, and there is XGBoost package which is using this regularized cost functions in the nodes of the tree. And some words about the variance. For gradient, for boosting, it doesn't matter if we take very dumb classifier like decision stamp. If we take a lot of these simple models, the result will be pretty good. So in case of begging of majority voting, we should take the models with smaller bias, so deep decision trees. In case of begging, we can use shallow decision trees, and it's better to use decision trees like depth 1, 2, 3, 4. If we take deeper trees, we'll get higher variance, unfortunately. We were talking about boosting with mean squared error loss function. But there are also different other loss functions like logistic regression, log loss, and in that case, there is no sense to use the error term for the second model. For example, in case of logistic regression, predictor y can be 1, predictor of our model can be -1, and then the difference, the error term, will give us 2, which is not the target of logistic regression. The other thing that could happen, that loss function could be very difficult to optimize. And so in 1999, the method of gradient boosting was proposed by Friedman. And now it's the most popular method in industry. So let's try to understand the idea behind this method. We still approximate our model by the sum of models, and we try to minimize our loss function. And to avoid the direct minimization problem, we can remember a little bit calculus. Let's draw the plot of loss function. Our goal is to minimize loss function. So if we have a value of loss function for the previous k models here, then we can calculate gradient, and it's obvious that we should go in the direction of negative gradient, or also people say anti-gradient, to minimize this loss function. And it means that if we shift our point by in the direction of anti-gradient, the result, the loss function, should be smaller than the previous than the result in the previous point. Of course, if we take a very large step, we can go over the minimum. So we can use also the factor eta. If we calculate this anti-gradient by the factor smaller than 1, then we can get more guarantee that we will not go far over the minimum of this function. So let's try to find the next model, model k plus 1. To approximate this shift. So this shift is given by the anti-gradient in the previous model with k summons, and the model k plus firsts will be built to approximate the anti-gradient. And to approximate just in this mean square error sense. As I mentioned, so this is the idea of gradient boosting. We use use the gradient of our loss function to build the next model instead of using the errors as in this previous simple boosting case. And if we use this learning rate factor, if it's the same for each step, then we can just factor out this rate, and we will get this final model for gradient boosting. There are several libraries for gradient boosting. There is also a library in scikit-learn, but nobody uses it because there are free libraries XGBoost. As I mentioned, it was written in 2016. Then LightGBoost from Microsoft, released in 2017, and CatBoost from Yandex, which works with categorical features, and it's useful if we don't want to take care about categorical data. Let's look. You can use any of these libraries. I will use today the light gradient boosting machine from Microsoft. Let's take our data set with prices. And you remember probably when we tried to apply linear regression with even with regularization to this data, we got like 0.6 accuracy. Now let's try to apply gradient boosting to this same data set. First of all, we split it into target and predictions, so eliminate target from our data. Then split into train and test. And also we need to, because I'm using not CatBoost, we need to apply one plot encoder to our categorical variable, the proximity to ocean. So after one plot encoding, we have this. And you remember, for trees, we don't need to scale. Let's use this LGBM regressor. There are many parameters that you can choose. By default, the number of leaves in trees is set to 31. It means that if we have 31 data points in one leaf, then we don't split this leaf. This parameter learning rate that I mentioned before, and number of estimators. You can also add regularizations, as you remember in extreme trees. That we saw in question 3. Okay, let's create this object and feed it. If we want to plot the training curve, then we can indicate this parameter evaluation set. So I will evaluate on the train and test sets. So overall score is 0.80, and you can see that it's a great improvement considering the linear model. And parameter plot metric allows you to plot the accuracy on depending on the iteration on the training and on the validation sets. I think the first should be the orange one should be training. Oh no, probably it's correct. Blue is training and orange one is validation. And also there is parameter importance, plot importance, which will show you importance of each feature. So let's use larger learning rate, and you will see that our model will overfit. The score is lower, and you can see that the accuracy goes up. To avoid overfit, there is also parameter early stopping. So this learning rate is important to avoid overfitting if we use a large number of simple models estimators. And the final remark about the importance feature evaluation. You remember that in linear models, the weights gave us the importance of the feature. In this case, we can take one feature, one column, and shuffle randomly numbers in this column and train our model on this data and see how the accuracy will decrease. And we can do this with each column. And if the accuracy decreases dramatically, then this feature probably is more important. So this is how can you evaluate the importance of feature in trees or in any actually model. So to conclude, I want to remind you that we have two main approaches for ensembles of models. One is the majority voting, when we take the most popular prediction for classification or mean value prediction for regression. And the second approach is boosting, when we train sequentially the models on the errors of the previous models. And in first case, it's important to take unbiased simple estimators. So it's better to take decision trees of depth 8, 9, or 10. While in the second case, it doesn't matter if the simple model is very biased. So we can take very shallow trees of depth 1 to 4 and still the model will eliminate these biases.